Picture this. You're strapped into a jet-powered car roaring across the Bonneville Salt Flats in Nevada. You're accelerating massively, pinned to your seat as the landscape just blurs past you. It's just you, the desert, and the sheer physics of motion. But suddenly, your dashboard shorts out.
So, if you're doing over 500 miles per hour and your speedometer completely dies, how could a simple line on a graph tell you your exact speed at exactly second 25 of your run? Well, this isn't just a theoretical puzzle. It's the exact reason why reading motion graphs is one of the absolute most powerful skills you can develop in physics. A graph isn't just a picture, it's a hidden code. And once you crack it, it reveals the exact story of an object's motion.
In today's explainer, here is what you'll master: reading displacement and velocity graphs, uncovering the formulas hidden right inside them, and tracking our jet car's journey using slopes and tangents.
Section 1. The Foundation, Bridging Math to Physics.
Okay, let's bridge the gap between the math you already know and the physics we're about to decode. On the left side, we've got your classic straight line equation from math class, right? Y equals mx plus b. The m is the slope, and the b is the y-intercept. Now glance over at the right side. In physics class, we write the equation for constant velocity motion as x equals x naught plus vt. Look at the perfect mirror happening here. The vertical axis y becomes our position x. The horizontal axis x becomes time t. Our y-intercept b becomes our initial starting position x naught, which leaves us with the absolute most important translation of all: the slope. The golden rule here is that the slope of a displacement versus time graph is velocity. Slope is just the rise, which is your change in displacement, divided by the run, which is your change in time. If you can find the slope of the line on your graph, boom, you've found the object's average velocity. It really is that straightforward. Let's see this in action using our jet car. On a straight line displacement graph, we just follow 3 simple steps. Step 1. Pick 2 widely separated points to be as accurate as possible. Let's say at 0.50 seconds, the car is at 525 meters, and at 6.40 seconds, it's way out at 2,000 meters. Step 2. Calculate rise over run. The rise is 2,000 minus 525. The run is 6.4 minus 0.5. That gives us 1,475 meters divided by 5.9 seconds. Step 3. Solve it out. That leaves us with an average velocity of 250 meters per second. And just to put that into perspective for a second, 250 meters per second is a staggering 560 miles per hour. That is massively faster than any highway speed limit, all pulled from a simple straight line on a graph. Section 2. The tangent line trick acceleration phase. Now here's where we hit a real-world complication. Jet cars don't just magically pop into existence doing 560 miles an hour. They have to accelerate to get there. So you might be asking, if the car is accelerating, the displacement graph won't be a straight line anymore. It's going to be a curve. So how on earth do we find the slope of a curved line to get our velocity? Think of reading a curved displacement graph like reading a map of a journey where someone keeps stepping harder and harder on the gas pedal. As time progresses, the slope of the curve gets steeper and steeper. Physically, a steeper slope just means a higher velocity. The speed is actively changing every single millisecond. This brings us to a really cool concept called instantaneous velocity. This is the exact speed of our jet car at one specific frozen moment in time. And to find it on a curved graph, we use the tangent line trick. You basically draw a perfectly straight line that just barely grazes the curve at your exact point of interest. The slope of that straight tangent line, that is your instantaneous velocity at that precise second. Let's use this to solve that question I hooked you with at the very beginning. Let's find the exact speed of the jet car at second 25 when the speedometer broke. Step 1. We go to our curve to displacement graph and draw a straight tangent line grazing the curve exactly at t equals 25 seconds. Step 2. We find the endpoints of that new straight tangent line. Looking at our graph, the line extends from 19 seconds at 1,300 meters up to 32 seconds at 3,120 meters. Step 3. We calculate the rise over run of this tangent line. 3,120 minus 1,300 gives us a rise of 1,820 meters. Divide that by the run of 13 seconds, and boom, we get exactly 140 meters per second. Problem solved using literally nothing but visual geometry. Section 3. Moving one level deeper, velocity and acceleration. Okay, quick check for you to lock this in. Let's see if you can spot the pattern.
If taking the slope of a position versus time graph gives us velocity, what do you think taking the slope of a velocity versus time graph gives us? If you guessed acceleration, you are absolutely right. The slope of a velocity versus time graph is acceleration. This is honestly what makes graphical analysis so incredibly cool. The mathematical rules just cascade downwards perfectly.
And this beautifully illustrates exactly why the formula for acceleration is what it is. Think about taking the slope of a velocity graph. Your rise is the change in velocity, or delta v. Your run is the change in time, or delta t. Well, change in velocity divided by change in time is the literal definition of acceleration.
So if we look at our jet car's velocity graph during its main acceleration phase, we see a perfectly straight upward line. If we calculate that slope, we find it's maintaining a massive, constant acceleration of 5.0 meters per second squared. That's literally half a g-force pressing the driver continuously back into their seat every single second.
Section 4. Hitting top speed. Acceleration drops. Let's connect this back to reality for a second. A car cannot accelerate forever. Eventually, aerodynamics and engine limits take over. As our jet car approaches its absolute top speed of 250 meters per second, it stops picking up speed quite as fast. The acceleration actually gradually decreases from that 5.0 meters per second squared, dropping all the way down to 0.
Wait, this is important. I really want you to picture the velocity graph right now in your head. What happens to the velocity graph line when the acceleration finally drops to absolute 0?
The velocity line becomes completely flat. Since the slope of the velocity graph is acceleration, an acceleration of 0 means a slope of 0, a perfectly flat horizontal line. You're no longer speeding up, you're not slowing down, you are just cruising, maintaining a constant top speed of 250 meters per second.
Section 5, the golden rules of graphs. Summary.
We've covered a lot of ground today, from flat salt flats to steep tangent lines. So here's your final review of the golden rules. First, the slope of a displacement graph is always your velocity. Second, if that displacement line is curved, your velocity is changing, meaning you're accelerating. Third, you can find the exact instantaneous velocity on a curve by taking the slope of a straight tangent line at that point. And fourth, if you take the slope of a velocity graph, you get the acceleration. These rules empower you to reverse engineer literally any motion. So I'll leave you with one final thought to ponder before our next explainer. We know an upward sloping velocity graph means the jet car is accelerating. But if a velocity graph is a straight line sloping steeply downwards, what exactly does that mean for our jet car's motion? And what would that feel like for the driver? Think about that negative slope.